This conference will now be recorded.
All right, welcome to our webinar. Today, Charlie Stillwell will talk about the decision support system developed by the USGS in cooperation with the North Carolina DOT. And I'll let Charlie take it away.
Sure, thank you, Greg. So this is a project that we completed about a year ago, myself and Greg and Curtis Weaver from the USGS in cooperation with Andy McDaniel, Ryan Mullins, and Brian Lipscomb of the North Carolina Department of Transportation worked on this. And we also had some meetings with the North Carolina Division of Environmental Quality. They're the regulators. So we kind of had a few stakeholders at the table during the development of this tool, which made it really useful for all parties. So first, I'll briefly introduce SELDM, which many of you are probably familiar with, but in case you're not, I'll go over that for about a minute. SELDM stands for the Stochastic Empirical Loading and Dilution Model, and it's a stormwater quality model that delivers meaningful information about the risk of adverse effects of runoff on receiving waters. And more specifically, this is the diagram that describes what's going on. In the top left, you can just see kind of a schematic of what SELDM does. It simulates rainfall and runoff events and the contributions from an upstream basin or stream that come in from the left, combined with the runoff from a highway or any impervious surface that then intersects with the stream, and you combine those to calculate downstream either loads or concentrations, dilution factors. There's a number of different ways you can spit out the data, but specifically looking at water quality in one of those regards. And what is unique about this water balance model is that it simulates many hundreds, can be over 1,000 events per simulation. And each of those rainfall events is developed using a distribution of likely scenarios. For instance, it's not always spitting in 1 inch of rain. It looks at a wide variety of rainfall events that are hitting the basin, that might be hitting the highway, and combines all those and then uses the statistics to develop a distribution of potential outputs downstream. So this is just an example, a screenshot of what an output from one scenario might look like. Each dot, either colored the blue plus sign or the orange circle, is the outcome of an event, where the blue is the concentration coming from the upstream basin. The orange might be the concentration downstream if there was no best management practice controlling runoff from the highway. And you can kind of see the effect of the highway on the downstream effects by looking at the differences between these dots. This is a pretty extreme example where there is an effect, but there's also many scenarios where the highway may not have an effect, or it has an effect without a BMP, but then with a BMP, you can see that that effect is mitigated. So SELDM is it's not an incredibly complex model, but depending on who's using it, it does require some training. And the North Carolina Department of Transportation wants a lot of their design engineers to be able to use SELDM, but we could not provide training to all the different consulting agencies and firms that might be working on their highway designs. So instead, the North Carolina DOT wanted to use SELDM as a base to develop more of a decision support tool, a little bit more user-friendly, that can still provide those data-driven stormwater treatment goals for any given highway project. So I'll walk through our specific set of work that was conducted for this project. First, we built a specific version of SELDM catered to North Carolina. That's what we called North Carolina SELDM. The next phase was we used North Carolina's version of SELDM to simulate over 100,000 different project scenarios. And then lastly, we used those 100,000 plus scenarios to build what we called a catalog, and now has become the NC SELDM decision support tool. And that is what I'll be giving a quick demonstration of at the end of the presentation. So as I described, SELDM takes into account upstream basin characteristics, estimates water quality concentrations from the upstream basin, combines it with the highway, and then estimates the effects downstream. So North Carolina SELDM refines from that and specifically uses North Carolina inputs. So we queried, I think it was 1,000 random basins using stream stats across the state of North Carolina, generated some distributions of likely basin sizes, physiographic regions. We looked at slopes, all sorts of these basin characteristics across the state to generate a useful list of those upstream basin, likelihoods that we would see in North Carolina roadway crossings. And then we also have, put in North Carolina specific data to generate those random rainfall and runoff events. So looking at precipitation data specific to North Carolina, stream flow data specific to North Carolina, water quality data specific to North Carolina. So we know that the results of the North Carolina version of SELDM are refined and catered to scenarios that we might see in North Carolina. So again, just going through some of these statistics, there's 266 stream gauges across the state, which we use to compute the stream flow statistics for each of the rainfall runoff scenarios. 57 stream gauges also had water quality information, which was used to develop water quality transport curves, basically telling us what is the expected concentration of a constituent as a function of the discharge in that stream. We have 7 highway runoff reports, which doesn't sound like a lot, but each of those reports contained a lot of different rainfall and runoff samples. In total, it was 25,000 event mean concentrations were added to the highway runoff database from those 7 runoff reports. So those informed the highway runoff water quality statistics. And lastly, 17 runoff BMP pairs were also used to understand the performance of specific BMPs in terms of water quality improvements and also water quantity improvements, such as mitigation of storm flow volumes or peak flow mitigation. So that effort was completed in, I believe, 2019, and we have a specific North Carolina version of SELDM. And the next step from there is to build a decision support tool using that as our foundation. So again, I'm just going to pull up this schematic to remind us of what specifically a SELDM scenario considers. First, we've got our characterization of upstream concentrations or loads in the storm flow. And you can imagine across North Carolina, we might have some streams up in the headwaters. Hopefully you can see my cursor, but either way, you can picture it. Up in the headwaters, we might have some bridge crossings that are way down in much larger streams. We may be in a forested area or maybe more urban areas, and every basin is different. And since every basin is different, we would expect to see different rainfall volumes, runoff volumes and runoff concentrations and water quality. Similarly, we could experience lots of different highway configurations. Are we talking about a 2-lane, 4-lane, larger highway? Is 1,000 feet in either direction from the bridge crossing draining to it, or tens of thousands of feet, or is it just a short stretch? What's the slope of that road? So all of these different scenarios are inputs to North Carolina SELDM, and we wanted to build a catalog of all of these possible combinations. So we came up with 112,320 hypothetical projects and built the catalog off of these scenarios. Those 112,320 scenarios were formed in conjunction with inputs from our contacts with the North Carolina Department of Transportation. So we looked at a factorial design, meaning each unique combination of 13 different drainage areas upstream, ranging from very small, I forget the smallest exactly, but it might have been 0.01 or 0.05 square miles, all the way up to a much larger drainage area like 100 or 100 plus square mile upstream basin contributing to the upstream loads. And we also looked at 3 different channel slopes, 4 different levels of imperviousness upstream, and did that all in 3 of the different physiographic regions of North Carolina. That's our mountains, Piedmont, and coast, which all have unique soil types and landscapes. So that gives us a total of 468 types of upstream basins we had considered. Likewise, for highways, we looked at 240 combinations, and we varied drainage area sizes, highway slopes, flow lengths, and most importantly was BMP type. So the 3 BMP types we looked at were runoff that was not treated by a BMP, runoff that is treated by what North Carolina calls minimum measures. That means generally like a typical roadside conveyance swale. And then also the BMP toolbox, which is a more involved type of best management practice, like a bioretention cell, for example. So in total, 468 upstream basins crossed with 240 highway combinations gives us that 112,000 that we were building a catalog off of. So for each of those 112,000-ish scenarios, we ran NC SELDM, and it gave us a bunch of statistics to go off of. Again, each of those scenarios had 30-ish years worth of rainfall events. So you can imagine that's a lot of data to sift through and build a catalog from. And that was our final challenge. So we built what we are calling the decision support tool, or the SELDM catalog, and it allows for hydraulic engineers to identify the scenario that most closely matches their highway project, and it returns the anticipated output, which is preliminary level of stormwater treatment required for a project. So at this point, I'm going to just do a quick demo and show you what is involved in our catalog. You can see right off the bat that the decision support tool was built in Excel. North Carolina Department of Transportation and a lot of their hydraulic engineers who work on designs are very familiar with Excel. So we felt comfortable using this as our platform. And this front page just shows some background information. We have a page with detailed instructions, but I'm going to skip that since I'm going to just show you. And this third tab is the inputs tab, where we really are going to be doing most of our work. So I'm just going to fill in some example project information. And let's see, sample site 1, and it's me. So the first step is to determine and characterize our upstream basin. So we use stream stats. North Carolina has these 6 and many more parameters available in stream stats. I'm fairly certain most of you will be familiar with the stream stats application, but I will just go ahead and show you just to be thorough. So I'm going to zoom us into a theoretical, this is not a real site, where we might have a highway construction project. So you can see that we are going to a point in stream stats where a roadway crossing is intersecting with a stream, and some length of this highway in this direction and some length of the highway in this direction is going to flow down, intersect, and discharge that runoff into the stream here. So I'm going to just first delineate this basin at the crossing. This will just take probably 5 or 10 seconds. Ten or 15 seconds. All right, so that's our basin, and all we need to do is continue on to this next step and get some of these basin characteristics. The specific ones we need are called the channel slope. That'll help inform us on the timing of when rainfall hits the basin and how long it will take to run off and intersect with the roadway. Also important is drainage area, of course, to help us figure out the timing and also volume of water that's coming from upstream. The next parameter we scroll down to is this LC11 IMP, which is the 2011 imperviousness. That's the most recent available in the North Carolina Stream Stats data set. And then lastly, we click on these percent region 1, 2, 3, and 4. This is really just to inform the user of which physiographic region this project is located in. Remember, the three options are the mountains out west, Piedmont in central North Carolina, and coastal plain. We actually have a fourth, but we've lumped them together in the coastal plain here. So again, this should just take a few seconds and a basin report will be generated where we can just open this up, scroll down, and we can see the actual values that we need to plug into the tool. So I'm just going to toggle between my screens here. You can see the first parameter code is channel slope. It was first alphabetically, first in the basin report, and we can just fill this in. 37.01 feet per mile is the channel slope. Drainage area, 2.71 miles. Our percent impervious is 5.1, and we are 100% in the Piedmont region. These will be 0. So that's the upstream basin. Next, we need to characterize the highway that is running off into the area of interest. And this is probably available at this stage in the preliminary designs. This tool is designed as more of a planning tool than as strictly a design tool in the later stages of the design. And this is more just to figure out what type of treatment might we need to anticipate when we advance in the design. So from preliminary designs, you can probably already know generally the impervious area, the slope of the highway, and the longest drainage length. You can even just, if you're going very roughly, you can even use tools still in this stream stats just to measure a length of highway that is draining to. You can turn on the national map layer, has topography, so you can estimate where that ridge line might be. Of course, it'd probably be better off of a preliminary design, but for the sake of this example, I just am making up some numbers here. I think that the total area draining to that might be 4.82 acres, about 3,000 feet on either side seems like the high point, and it'd be maybe a 2-lane highway with some wide shoulders in this fake example. The highway slope draining towards the stream was about 2.25%, and the length of the longest flow path was about 3,500 feet. So with all of our basin inputs and all of our highway design inputs, you can see an output was automatically generated, and the suggested level of treatment, at least based on these preliminary assessments, is the minimum measures. Remembering in North Carolina lingo, that basically means your roadside swale. And the way that this tool works is it automatically generates this output. I'm just going to fill in a fake example. Let's say it was becoming a 4-lane highway instead of just a 2-lane with shoulders. So it's about double the drainage area. This output would automatically update, and you can see there's more runoff from the highway contributing. Thus, there's a larger impact downstream, and that's reflected in the changed output, which is now showing a BMP toolbox. A BMP from the BMP toolbox may be necessary to treat stormwater runoff at that site. We tried our best to try to avoid any errors that would throw off the results. So for instance, I'm going to make the sum of the regions over 100. That would give us an error. We don't want that. If I were to make this a negative number accidentally, it would give us an error. So we've tried to make it as user-friendly and impossible to make errors as we could. So that's the input sheet. Everything in there is then auto-filled into the summary report, which just copies all the project information, gives the recommendation and a brief explanation. And I'll just go into print preview mode. You can see this nicely fits on one page, which can be saved and submitted to whoever the regulatory agent is, or just stored for project planning purposes later on down the road. The workbook also includes some example projects, not the same ones I showed you, but some examples that step through exactly how you would generate a summary report. So in the background, there's a lot happening. As you can understand, with all the different scenarios we ran and all the different rainfall events within each scenario, there's a lot happening in the background, but we try to make it as user-friendly as we can for the hydraulic engineer. So I'll just take another couple of minutes to describe what is happening in the background so you have a better understanding. First, by putting in all the basin inputs and the highway inputs, we are querying which of the 112,320 scenarios or different combinations of an upstream basin and a highway most closely match the inputs for that specific project. So it searches through that 112,000 and generates the closest match. And then from there, it pulls the summary statistic that is generated from each of the 1,500 events for that specific scenario. And then we basically ask a yes or no question of that summary statistic. Does the untreated runoff cause the QW10 statistic to be 25% or more? QW10 is a statistic we generated in cooperation with the regulators and DOT. Basically, what we have done is ranked all 1,500 rainfall runoff events, found the 10th percentile of events with the largest change. So it's a conservative estimate of downstream increases to concentration. And we basically ask the yes or no question of, is the 10% worst storm in terms of downstream concentration change greater than a 25% increase in that constituent? If it is increased but less than 25%, we say that the preliminary treatment necessary the preliminary treatment is not necessary per the science. Basically what this does is we're looking at a mass balance model. So every scenario is going to tell you some percent increase, but a lot of those percent increases are not substantial. We arrived at 25% as a substantial change based on those conversations with the regulator. So if it's less than 25% in that conservative example of the 10th percentile worst, we say that direct discharge might be okay in that scenario. If it is greater than 25% change downstream, then we have to ask another set of questions and first treat that runoff using the minimum measures. So that's going through the roadside swale or the open drain. And if that still increases water quality by greater than 25%, that would be the yes, and we require something from the BMP toolbox. If it's less than that 25% threshold, the preliminary treatment recommendation would be the minimum measures. So it really is just a nested set of yes or no questions based on how substantial we have defined the changes to downstream water quality. So the decision support tool has been in use for probably not quite a year, but pretty close. And from what we've heard from our contacts at North Carolina Department of Transportation, they're listed below, these bottom three. We've heard a lot of positive feedback. The tool's been easy to use. The regulator, since they worked with us on the project, they know what to expect. And it has really streamlined that communication between the hydraulic engineers and the regulators, which has been very successful. And this tool is now an official step in the workflow of the NPDES permitting process. So I don't know how many times it's been used yet, but every project that's in this stage of preliminary design across the state of North Carolina has to use the tool. And so far it's been quite successful from what we found. And it's been a pleasure working with the folks at DOT. So thank you very much for your time. I have left plenty of time for questions, I believe. So, and also, Greg, if you want to add anything, feel free.
All right, great. I was just going to mention that 25% might seem large, but when you look at, there's this couple studies in the literature that shows that, if you're trying to measure a difference in water quality, especially stormwater, that, the uncertainties of a stormwater measurement can be as much as plus or minus 100%. And, if people are doing a good job monitoring, it's within 25%. So that's where that number came from.
Yeah,
All right.
it's kind of analogous to like a confidence level threshold based on the uncertainty of just water quality data as a whole.
Exactly. Yes. Well, thank you, Charlie. I'm gonna take us off record. I'm gonna unmute everybody and then give people the floor for questions.
Sure.
All right. Thank you again, Charlie.